Hello everyone. Welcome in this video. Today we are going to find out the weight of a body at the center of the earth, and in doing so we will also understand gravitation in much more detail. Let's get started. Let's say this is the earth, and this is the International Space Station, which is located in space. Now we see videos of astronauts in the International Space Station who are in a state of weightlessness, and they just float in the International Space Station. Well, the reason is that there is no gravity in the ISS. However, on the surface of the Earth, we feel our weight. Because there is gravity on the surface of the Earth. So as we go higher from the Earth, the acceleration due to gravity, or rather gravity, decreases. So that's why in the ISS there is zero gravity, and so the astronauts appear to be in a state of weightlessness. Well, this behavior of gravity is governed by the universal law of gravitation, which states that the force experienced by a body uh, is equal to G into capital M into small m by r square, where m is the mass of the earth, small m is the force experienced by a body, the gravitational force which is experienced by the body. So the mass of that body, that is m. R is the distance of this body from the center of the earth. So this distance is r, and g is called universal gravitation constant, and the value of g is 6.67 into 10 to the power minus 11 Newton meter square by kg square. Let's rewrite this equation as this in this form, and we know that our weight is equal to mg, where m is our mass and g is the acceleration due to gravity. So from this equation, the acceleration due to gravity is equal to capital G, which is the gravitational constant, into mass of Earth divided by r square. So this equation tells us that the acceleration due to gravity is inversely proportional to the square of the distance of the body from the center of the earth, which means that if the body is far away from the center of the earth, the acceleration due to gravity experienced by the body will be less, whereas if the body is very close to the surface of to the center of the earth, the value of g will be very high. Now what if an object is at the center of the earth? Well, in that case, the value of r will be 0, and by this equation g will be infinite, and hence the weight of the body will be infinite or very high. Well, is that the case? No. The reason is that this acceleration due to gravity g, it behaves differently when an object is outside the earth than when the object is inside the earth. So this equation is valid when the object is outside the earth. Now we'll understand how g will behave when an object is placed inside the earth. Okay. So before we move forward, let's understand the concept of gravitational field. Well, a gravitational field is the space around a body in which another body experiences a force of gravitational attraction. So let's say this is the earth. So gravitational field of the earth is the space around earth where another body which is in the field experiences a force of gravitational attraction. Now this space has its own existence and has energy and momentum, and this gravitational field, it is a vector quantity, and the intensity of the gravitational field is defined by E vector. Okay, it's rather denoted by E vector, and it is defined as the ratio of the force experienced by a body in the gravitational field to the mass of the body. So this is how it is defined. The gravitational field is defined. So let's say this is the earth and this is an object in the gravitational field of the earth. So the gravitational field of the Earth on this object, which is at a distance of r from the center of the Earth and of course outside the Earth, will be given by F vector, which is F is the gravitational force experienced by this object divided by the mass of the object, which will be G capital M by R square. Now we will calculate the value of E, the gravitational field, inside the surface of the Earth. Now, since Earth is a sphere, so sphere is a it's a bit complex it's a bit complex object. So to simplify our calculation, we will first find out the gravitational field of a ring on an object which is at a distance of r from the center of the ring, and then we will extrapolate the result of this calculation into a sphere. So let's do it in a two-step process to simplify our calculation. So let's say we have a ring and the mass of the ring is capital M, and let's say an object of mass small m is situated at a distance of small r from the center of the ring. So let's find out the gravitational field of the ring on the object of mass small m. So let's denote. So let's assume. So let's consider a small a small mass dm here on the ring. So what we will do is we will calculate the gravitational field because of the small mass dm on this object, and then we will sum or rather integrate this over the entire ring to calculate the gravitational field of the entire ring. So because of the small mass dm, what will be the gravitational field? The gravitational field will be mass into g, we are just following this equation, divided by r. So here r is the distance of this object from this small mass dm, which is z, which is dm g z square. Now as I told that this E is a vector, so the direction of E will be in this direction. Okay, so we can split it into two components, vertical and horizontal. Okay, now as we can see, because of symmetry, let's say if we consider a similar small dm here, just diametrically opposite. So because of symmetry, all the vertical component of E will cancel out each other. So only the component of E along the axis of the ring will be there. Okay. So what will be the component of this gravitational field along the axis? So that will be this whole term into cos theta, right? So this is the gravitational field of this small, element of this ring on this object. Now, if we integrate it over the entire ring, then we get the gravitational field of the ring on this object is capital mg divided by z square into cos theta. Now, this result is very important. Well, now we know the gravitational field of a ring at an object P. So now let's extend this result further, and let's try to find out the gravitational field of a hollow spherical shell on an object P. And once we are able to find out, once we have the result of this hollow spherical shell, we will extrapolate this result to find out the gravitational field of a solid sphere, which we will assume and we'll assume that Earth is a solid sphere, and then after that we will be in a better position to find out the weight of an object at the center of the Earth. So let's assume that this hollow spherical shell is composed of lots of small rings. So here I have drawn one elementary ring A dash. So let's say this hollow spherical shell is composed of lots of rings, lots of rings. So the gravitational field of the hollow spherical shell on this object point P will be the sum of the gravitational field of all these elementary rings. So integrate the gravitational field due to these rings and find out the gravitational field of the spherical shell. So let's find out the gravitational field due to this ring A dash. Now before that, let's understand the nomenclature here. So small a is the radius of the spherical shell. This P is the object where we are going to find out the gravitational field. This object is situated at a distance of r. So at a distance of r from the center of the and the angle which this ring subtends at the center of the sphere is theta, and the angle which this elementary ring subtends at this object P is alpha. So let's find out the gravitational field due to this ring. So before that, let's find out the mass of this ring. So and let's denote the mass as dm. Okay. So before finding the mass, let's find out the area of this elementary ring. So what will be the area of this elementary ring? The area of this ring will be the width the ring in the perimeter of the ring. What will be the width of the ring? The width of the ring will be AA. What will be AA dash? AA dash will be, from geometry as we can see, A into this angle, and this, if this angle is theta, then this elementary angle will be d theta. So AA dash will be A d theta. What will be the perimeter? Perimeter will be 2 pi r. So what will be the radius of this elementary ring? The radius will be AQ. What will be AQ? AQ will be A sine theta. Okay, so area is the now let's assume that this spherical shell has a uniform mass per unit area. So what is the mass per unit area? So let's say the mass of this spherical shell is capital. So the mass per unit area will be capital M by 4 pi a square. And so what will be the mass of this elementary ring? Capital M by 4 pi a square into A, which is and if we simplify further, the mass of the elementary ring will be M by 2 sine theta d theta. And we know from our previous result that the gravitational field due to a ring is given by G dm, G into mass divided by Z square into cos alpha. So this, we are simply extending our previous result and replace it with the nomenclature we have used here. So if we replace these values, we'll get the gravitational field due to this elementary ring on the object P is G m by 2 sine theta d theta cos alpha Z square. So now once we have this equation of dE in terms of theta, alpha and Z square. So now we want this equation to be in terms of Z only. Okay. So let's replace theta and alpha with Z. So just follow these mathematical steps. If we do so, we get dE is equal to Gm by 4 AR square into this term. So we have this equation for the gravitational field. Now let's try to extrapolate this result, or rather integrate this result over the entire spherical hollow sphere. Now as we can see, there are two cases. Case 1, this object P is outside the sphere, and case 2, this object P is inside the sphere. Now in both these situations, the value of Z, or rather the limits of Z, will be different. So take for case when P is outside the sphere. When P is outside the sphere, what is the range of values which this Z can take? So the range of values which Z can take will be R minus A to R plus A. Now let's say how. Now what can be the minimum value of Z? The minimum value of Z will be for an elementary ring which is just near point M. Okay, then the value of Z will be Pm, which is equal to R minus A. Okay, that's what I've written. What can be the maximum value of Z? The maximum value of Z will be again for an elementary ring here, somewhere around here. So in that case, what will be the value of Z? That Z will be R plus A. So if we put this value of Z, put this range, we get E is equal to Gm by R square for outside the sphere. Okay. Now let's find out what is the value of E inside the sphere. Now assume case 2 when this object P is inside the sphere. So when this P is inside the sphere, so again our equation for gravitational field will remain same, but range of the value of Z will be different. Okay. So what will be the range of value of Z? So the maximum value of Z will be for an elementary ring which is somewhere around here. So let's say somewhere around here we have a ring. So this will have the maximum value of Z, and the minimum value of Z will be for an elementary ring which is, let's say, somewhere around here, very small ring close to point B. So this will be the the PB will be the value of Z. So the range of Z in this case will be PB is the minimum, PA is the maximum. So PB is equal to what? A is the radius of this hollow sphere, A minus R, and PA is A plus R. Now if you put these ranges and if you integrate it over Z, you will get E is equal to 0. Right. So if it is not clear to you, just pause this video and again think through it, and also try to solve this integration on your own, which I hope you should be comfortable with. So if you have doubt solving integration, just refer my first video, because as I mentioned, you have to be good in mathematics. You want to excel in physics, because mathematics is the language of physics. So you will have to be comfortable with integration. So yeah, so this result is incredible. So the value of the gravitational field inside a hollow sphere is 0, right? So now let's extrapolate this result to find out the value of gravitational field of a solid sphere. So now we have the result of the gravitational field due to a spherical shell. So now again, now let's extend this result to find out the gravitational field due to a solid sphere. So let's assume that our Earth is a solid sphere, and let's say there's an object P outside Earth at a distance of r from the center of the Earth. Now we will assume that this Earth is the solid sphere, which is Earth, is an integration of lots of uh, elementary hollow spherical shells inside the I mean lots of, forget inside, lots of the, basically this solid sphere is an integration of elementary spherical shell. Okay, so let's consider one such elementary spherical shell inside the Earth, and there will be many such spherical shells. So we will integrate our result of over one spherical shell to obtain to obtain the gravitational field due to this, this solid sphere, which is our Earth. So let's consider this elementary spherical shell here. So we know that the gravitational field due to an elementary spherical shell on an object outside the shell is given by g times mass of the shell divided by r square. So in this case, let's assume that this mass of this shell is dm. So this dE, the gravitational field due to this small spherical shell will be given by g dm by r square, and if we integrate this mass over the entire mass of the Earth, we get the gravitational field due to Earth is g capital M r square, right, for objects situated outside Earth. So this result we have seen earlier. So this result, the theory of gravitation also says this thing only, right? The theory of gravitation says that the force experienced by an object is equal. The gravitational force experienced by an object due to Earth is gm small m by r square, and so the acceleration due to gravity is mg. And so the acceleration due to gravity is gm by r square. So this acceleration due to gravity, or gravitational field, are nothing but same. So this result we knew earlier. Now let's understand what will be the gravitational field inside the surface of the Earth. Now let's assume that this point P is situated inside the Earth. Okay. So to find the gravitational field on this point P, again consider elementary spherical shells. Now here, in this situation, there will be two kinds of spherical shells. For one set of spherical shells, as denoted by this red color, this point P is situated outside them. However, for these spherical shells, as denoted by this yellow color, this point P is situated inside them. So the gravitational field due to these yellow spherical shells on this point P will be 0. So to calculate the gravitational field on point P, we will only consider the spherical shells for which this point P is outside. So let's take any such shell, and so the gravitational field due to this any such shell on this point P will be g dm by r square. Now let's integrate it over those spherical shells which lie inside point P. So if we integrate this particular gravitational field over those spherical shells, we will get g by r square into integration of dm. So here we will consider only those masses which fall inside point P. So once we integrate that, these masses, we will ultimately get the mass. We'll have to find out the mass of this solid sphere of radius small r. So what will be the mass of this solid sphere of radius small r? So to do so, let's assume that the mass of the Earth is capital M, and let's assume that the Earth is having uniform mass per unit volume. So what is the volume of Earth? So volume of Earth is 4 by 3 pi a cube, because a is the radius of the Earth. So the mass per unit volume of Earth will be capital M by 4 by 3 pi a cube. So what will be the what will be the mass of this solid of radius small r? It will be m by a cube into r cube. So if we put this term here, we will get the gravitational field on this point P situated at a distance of r from the center of the earth inside the earth. So if we put these terms, we ultimately get the gravitational field on point P as gm small r divided by a cube, right? So this is the gravitational field P situated at the earth. Now let's plot the gravitational field or acceleration due to gravity versus r. So as you can see, when r is less than equal to a, so let's say r is rather less than a, we have the value of E is equal to gm r by a cube. So essentially this, if we plot this equation, it will be a straight line passing through origin, and when r becomes more than, the graph will be somewhat like this. Okay, so what does this graph show? This graph shows that at the center of the earth, which means when r is equal to 0, the gravitational field is also 0. Then as the object moves away from the center of the earth and reaches the surface of the earth, the gravitational field increases linearly. Now as the object goes away from the surface of the earth, the gravitational field then starts decreasing, and ultimately when the object in space, the gravitational field becomes 0. So that's why astronauts in International Space Station, so they appear in a state of weightlessness, and because the gravitational field there is 0. Yeah, so our first question was, what is the weight of an object at the center of the earth? So as we can see from this graph, at the center of the earth, the gravitational field is 0. So what will be the gravitational force experienced by the object at the center of the earth? That will be mass times the gravitational field. So since E is 0, so the gravitational force experienced by an object at the center of the earth will be 0. Well, of course, here we have made an assumption that the earth is uniform, and the mass of the earth is also uniform. But in this situation, well, yes, the weight of the object will be 0. So hope you like this video, and I hope that your concept of gravitation is now clear. So I'll catch up with you in the next video. Thanks for watching.